Section 2.2 is about graphs of functions. Okay. Most important way to visualize a function is through its graph. So we're going to talk more about graphing functions. Okay. Now, most people think that the best way to graph a function is just plug it in the calculator and hit enter. And that is a good way. It's not the only way that I want you to know about, though. Okay. A graph of a function gives a picture of the behavior or life history of the function. We can read the value of f of x from the graph as being the height above the graph from the point x. Okay. A convenient way to graph a function is to use a graphing calculator. That's what I talked about a minute ago. It's just not the only way. It's just a convenient way. Okay. When we're graphing, we use y to be f of x. Depending on what kind of calculator you have, it might say y equals or it might say f of x equals. You know that those two are for us, are equivalent. Okay. All right. So what if it says sketch the graph of the function by first making a table of values? Okay. Well, if we're sketching the graph of the function by first making a table of values, thinking about back to last section where we evaluated functions, isn't that all we're doing here? Are we taking -4 and plugging it into the function? -4 plus 4. So 4 plus minus a negative is 4. So 4 plus 4 is 8. If it's -3, I have a -3 plus 4. 3 plus 4. Well, that's 7. Okay. What if it's 0? If x is 0, -0, it's just 4. Okay. What if it's 1? -1 plus 4. Well, -1 plus 4 is 3. If x is if x is 3, I get -3 plus 4 because of the negative that's built into the problem. Okay. -3 plus 4 is 1. And 4, -4 plus 4, well, that's 0. Okay. Now to graph this function, obviously the convenient thing to do would be using your graphing calculator. But if it says sketch the graph, we actually want to take a piece of graph paper and plot these points out. That's the whole purpose of us making the table. Because will we always have a graphing calculator? Maybe. We'll always have a calculator because we have our phone. But I don't know if we'll always have a graphing calculator. So we need to make sure we understand how to do this. Okay. So I'm going to draw an axis in here, x-axis and a y-axis, and then we'll plot the points. -4, 1, 2, 3, 4, 8. 1, 2, 3, 4, 5, 6, 7, 8. If x is -3, y is 7. If x is 0, y is 4. If x is 1, y is 3. If x is 3, y is 1. And if x is 4, y is 0. Okay? Hopefully you can see that that makes a line. We knew it was going to be a line because it didn't have any exponents here in our problem. And there's no other symbols like radicals or anything like that. Okay, so there's our line. That's the sketch of our graph. Okay. Graphing piecewise functions. Piecewise functions is defined by different formulas on different parts of the domain. We actually talked about a piecewise function in the last section that we did. I just didn't call it by name because it wasn't quite time yet. Okay, so now it's time, so I'm going to call it by name. It's a piecewise function. It's pieces and parts of different equations, okay, changed on different parts of the domain. So in this function, the piecewise function says our function is equal to a parabola, parent function in fact, when x is greater or less than or equal to 1, and x is a line, 2x plus 1, if x is greater than 1. Okay, so this right here, this line right here, the x equals 1, this line is kind of our dividing line. It's our changing line. Okay, the parabola, the parent function parabola, is here. Because 1 squared is 1, 2 squared is 4, 3 squared is 9, which I think is there. 1, 2, 3, 4, 5, 6, 7, 8, 9, right there. Okay. We know parabolas are symmetric, so I'm going to draw that real quick. Well, it's only a parabola where this line, where x is less than or equal to this line. So it's only part of the function right there. Okay. Didn't go low enough. Sorry about that. That's a little better. Okay. But it's the equation of this line on the right side of this line right here, on the right side of the line, x equals 1. So it's 2x plus 1. Well, 2x plus 1, I'd rise 1 for my y-intercept, then rise 2, run 1, rise 2, run 1, rise 2, run 1, rise 2, run 1. Okay? It's not defined here because that's on the line 1, but it is defined all the rest of this. Now, that line goes all the way here, right? But this part is not defined for this particular function. This line is only defined when x is greater than 1. Okay? Well, what about this one? The graph of an absolute value function can be viewed as a piecewise function because it's the line x when x is greater than or equal to 0, and it's the line negative x if x is less than 0. So here that changing line, the boundary kind of thing, is right here, is on the y-axis. So it's the line y equals x, which is this line right here. It's defined here like that for everything greater than x. Okay, now we know that the line goes all the way down here, but it's not defined there, so we don't draw it there. Okay, now we know it's the line negative x, so rise 1, run 1 backwards, right here on the left side of the line x equals 0, right here. So it's not defined at 0, except we don't have to worry about that this time because it is defined on that exact point for here. So I know it's this way. Now, if I take these together, that's our absolute value function. But I can rewrite it as a piecewise function, this part for greater than 0, this part for less than 0. Okay? Now, vertical line tests will help us know if something's a function or not. Okay? So first of all, a curve in the coordinate plane is the graph of a function if and only if no vertical line intersects the curve more than once. So what we need to be able to do is we need to be able to look at graphs like this and decide if they are functions or not. It's basically a yes or no question. Is it a function or not? And we can use the vertical line test. A lot of people call it the pencil test. Well, that's on marker. This is a pencil. Okay? Because we can treat this as a vertical line. We pull it across. Okay? And we look and we say, does this function right here, or does this graph, excuse me, we don't know if it's a function or not yet, as I pull my vertical line across, is it touching the function in more than one place? If it does, like this dotted line that's here, do you see how it touches the function here and here? It touches the function, the vertical line, at more than one place, so this is not a function. If on the second example, example B, if I pull my vertical line or my pen across the page, notice as I'm pulling across the page, it's only ever touching the function in one place. So that is a function. Right now, all I know about these are they are relations, but I can define it as a function or not. Yes, a function, no, not, based on if it passes the vertical line test. Okay, so yes, and well, right here, it's actually touching in 3 different places. That's definitely not a function. Okay? All right. Any equation in the variables x and y defines a relationship between these variables. So for example, the equation y equals x, or y minus x squared equals 0 defines a relationship between y and x. We're not saying it's necessarily a function. We are saying it's a relationship, and we're trying to figure out what defines a function. Okay? This is an equation, so I know it has a relationship because these two are together, there's an equal sign and things like that. Okay? So does the equation define y as a function of x? So to find out, we solve for y in this problem right here, y minus x squared equals 0. We solve for y by adding x squared to both sides to get y equals x squared. We see the equation defines a rule or a function, y equals x squared, that gives one value of y for every value of x. Now, we talked earlier about the fact that it is a function if for every value of x there is only one y, okay? So we know that this is a function. Because we know it's a function, we can write it in function notation, which is f of x, as opposed to y, okay? So, two examples. Does the equation define y as a function of x? Well, let's see. If we start here, we got to get it equal to y. So we add x squared to both sides. So this gives us y equals x squared plus 2. Well, y equals x squared plus 2, that defines y as a function of x. So yes, this is a function. Okay? Now look at this one. If I have to solve for y, I would have to subtract x on both sides. Subtract x squared on both sides. I would get y squared equals negative x squared plus 4, or 4 minus x squared, either one is fine. But then to solve for y, I would have to actually square root both sides. When I do that, I get y equals plus or minus the square root of negative x squared plus 4. So if I put in an x value here, I'm going to get a y value. But if I put in a different x value, I'll get a different y value. So how do I decide if this is a function or not? Okay. This one's not a function. First of all, if you think back to a couple days ago when we talked about circles, we know that this is a circle because it's x squared plus y squared. We know the shape of the circle looks like that, and we know that is not a function. For every x value, there's two y values. No matter what x value I put in here, I'm going to get a positive or negative. I'm going to get two different values for y when I put in an x value. So I know that that is not a function. Okay? All right, linear functions and their graphs. F of x equals mx plus b. Y equals mx plus b. We've talked about that several times already this semester. Okay? We know that if it's just f of x or just y equaling a constant number, I know that's a constant line. A horizontal line goes straight across the page. Okay? Now, b would be the intercept. That's how we name it. It's like which axis is it crossing and where. Okay? Now this one's different because it has mx plus b. It has a slope. It has b. B is the intercept where it crosses the axis. Okay? Only difference is this has a slope. This one doesn't. It's zero slope. Okay? Power functions and their graphs. So x to the n power. Well, x squared, those are quadratics. We've talked about those a little bit. We know those look like parabolas. X to the third power, this is what it looks like. Okay. X to the fourth power looks very similar to a parabola, but not quite exactly the same. There's actually a little bump in there you can't really see. And then x to the fifth, again, looks a lot like x to the third power. Okay. It's a little bit longer in here. Notice that these are even powers. Both ends go in the same direction. These are odd powers. Both ends go in opposite directions. Okay? Let's see, root functions. Okay? Square root function. Cube root function goes both directions. Fourth root function just, so very similar to a square root. Fifth root function goes both directions. So again, very similar to a cube root function. Okay? Reciprocal functions. Sometimes these are called rational functions because they look like fractions. 1 over x, two parts, opposite sides of the x-axis. 1 over x squared, two parts, but on the same side of the x-axis. Okay? Absolute value functions. Well, we just talked about absolute value a second ago when we were talking about piecewise functions. We know this looks like a v. Absolute value looks like a v. Okay? I wanted you to be aware of those. Those are going to show up in some of your activities, so I wanted you to be able to know by name what those were called. Okay? Peace.